we can right now start. This is, as said, we have done as GMI a lot of webinar, myself and Bob. This is the first time we are doing the webinar together. So if you may see some small mistake in handling, please accept my apologies. And now, okay, we can go ahead. I ask the control of the presentation. Before to enter in the heart, I would like to go through a very short introduction of GMI. Let me check if the control is running, and yes, exactly. This is happening all the time, and I'm not able to have the control of the presentation. So
it should happen here in just a second.
Yes, I know, because then what I expect is to see 3-4 pages running in a shot. Okay, in fact, here it is. Okay, some small detail, or let me say introduction of the speakers. Bob Johnson, I will give him then the chance to say some word about him. I am Mauro Perego. I am sales director for GMI. As said, give me a few minutes, a few seconds to have an introduction what GMI is doing. GMI is a company who is designing and producing field device equipment which are part of most of the automation package known as DCS, ESD, firing gas, and so on. GMI is an Italian company which is present, who is present worldwide in 5 continents. It's Italian. We design and produce here in Italy, but of course we will see later we are also present worldwide. What we do, we focus with our product our attention to safety, and we cover mainly 2 aspects of safety. The first is intrinsic safety, and the second is functional safety. Most of the webinar we are handling are on these 2 subjects. Today we focus with Bob our attention on intrinsic safety. This is just an overview of the product we have. We have barrier, we have safety relays, we have isolators, we have power supply, as well as multiplexer. All of these equipment are either certified for intrinsic safety application and or are certified for functional safety. That means up to level SEAL 3 of functional safety. But functional safety will be the subject of other webinars, so I'm not going to discuss it here. We have termination board because we have customized termination board where our relays and our barrier or isolator are installed and connected. I don't know what happened. I have lost my control.
I think it was me. I accidentally hit my mouse.
No problem. Anyway, I was finished with that slide. I want just to mention that we have one department which is dedicated to consultancy and training for functional safety, and very soon we will extend also our departments, including dedicated department for intrinsic safety. And we will be able then to provide consultancies and dedicated training with the certification scheme process and so on and so on. As said, we are Italian, but we are present worldwide with subsidiaries, with distributors, with offices around the world. And I'm not sure, can you go ahead, because I have lost my control now, Bob. Okay.
Yeah.
This is just a limited list of customer, typical customer we have: system vendor, EPC contractor, OEM, end users, and so on and so on. You will receive, what I didn't say, you will receive copy of this presentation in PDF format, so you can go through with the and you can enter in any details you are interested to. And also this webinar, as well as all other webinars we are running, are available on our YouTube channel. So you can, if there is something that you want to review, you have this chance later on. So we can go ahead, Bob, because okay, it's my short introduction is over. As said, you have the chance with question and answer if you want to raise answer, and then I leave now the speech to Bob, so we can enter into the heart of the presentation.
Awesome. Thank you, Mauro. Thank you very much. And good morning, good evening, good afternoon. As Mauro said, it's very early here in Houston, Texas. I hope all of you around the world are all COVID-free and everything is going okay with the virus. Fortunately, we've had some good news here in Texas. We were one of the hot spots here in the United States, but it seems to have kind of calmed down here over the last 2 weeks. So we're still wearing masks and doing all the social distancing, and school is starting up virtually. So hopefully we'll get some sort of vaccine for all this and we can get back to normal. And on top of that, we have a hurricane forming in the Gulf of Mexico. So we'll have a hurricane to deal with here in the next 2 days or so. So hopefully everything will work out okay. So intrinsic safety, 6 common mistakes. So as Mauro mentioned, I don't work for GMI. I'm actually a distributor for GMI in Houston. And part of what we do, besides being a distributor, we're also a training organization under the IECEX Certificate of Personnel Competency Program. And I'm also what is called a COMPEX instructor as well. So we train people on the competency issues, and we also do inspections. And one of the things when I was talking with GMI about a potential topic for a seminar was what are some of the faults that we see when we go out and we do inspections of IS installations. And so we figured that would be something that would be good to discuss because it's somewhat that is near and dear to my heart, and it's something I certainly see quite a bit. So let's start off a little bit. What are the standards, the regulations that we follow for our installation and design of intrinsically safe circuits? Within the United States, we follow the NFPA 70, which is commonly referred to as the National Electric Code. Canada has their version called the CEC. And then, of course, there's international standards that are referenced. Primarily, the ones that we really follow for design and install of IS systems are the -14, which is for all electrical EX equipment, not just IS, but we follow that for other protection concepts as well. The -17 standard, which is an inspection standard. And then there's also what is called -25, which is our intrinsically safe electrical systems. So those 3 different IEC standards are really key for knowledge and understanding what we should be doing when we're designing intrinsically safe systems. Now, there is another IEC standard that deals specifically on the design of intrinsically safe products, which is the -11 standard. As a designer, as a panel builder, the -11 standard is not necessarily something that you really need to get into deeply, if you will, because that's what the manufacturers must follow. So we don't really follow that for this webinar. We're really following the installation standards and design standards. So as I mentioned there, these are some of the relevant standards. As I mentioned, the IEC standards in Europe, we follow the EN version of the 60079 set of standards. And sometimes people have questions, what's the difference between the IEC standard and the EN version? They are identical, if you will, from the base of the standard itself. The IEC develops the standard. CENELEC, which is the standard writing organization within Europe, introduces it as an EN version, and then it's up to each country within Europe to adopt it as their country standard. Now, there are national annexes You could find also there's a difference between the IEC standard and the EN standard in relevant references to relevant standards, but the base document, if you will, the standard, if you will, is identical. Some of the other standards you might run into if you're doing design work, you might find API, recommended practices, which is commonly used in the offshore market. There's also other IEC standards. The 61892 standards deal specifically with mobile and fixed offshore units. Hazardous locations is the -7 standard, so there's also reference to intrinsic safety in all of those as well. So the good thing to know is the standards, if you will, and the design criteria from many of these different documents are all very, very similar. As a matter of fact, in some cases, they're virtually identical. So if you understand the base information of say, what comes out of -14 from the design of an EX installation, you can apply that, the basics to pretty much anywhere in the world, which is a positive thing.
Okay.
So, I have a question here, Mauro. I don't know if
Yeah.
you can launch it.
We are looking for some feedback from the participant. So we launch our first polling, and we would like to know from you what is about your knowledge. What is the international installation standard recognized for installation and design of intrinsic safe systems? I think.
Yeah, we'll give it a minute here to see kind of if you guys were paying attention.
Okay.
Good, we're getting some answers in.
Yes, we see some answer.
Let's give another 10 seconds, Mauro, maybe, and then we can share the results.
Yes, let me, okay, just few seconds again, and I stop the polling. We have a good rate of feedback at the moment. Let me stop, and I share the result. You all should see the result of this polling. Does it say something to you, Bob?
Yeah, well, you know, it's somewhat of a trick question, because you could argue that the international installation standard, if we want to be, you know, what I would consider to be international may not necessarily be what you would consider to be international, but the correct answer for this would be the -14 standard. So that is our design standard. Now the 25 kind of bolts on to the -14 standard. Again, the 17 standard is our inspections. The CSA and the NFPA documents are considered domestic installation standards. So because I'm coming at it from a North American standpoint, so the most correct answer would be the -14. And Mauro, we did have one question from Carl. If we follow the 60079, are we compliant for installations in the US and the NFPA? Yes and no. Ultimately, we do have to follow the NFPA 70 document with regards to installations in the United States. However, we will, as we talk about a little bit, the requirements within the National Electric Code, and specifically all the details with regards to installation and design of IS falls within Article 504. And for the most part, that's where the meat of the installation details are located within the National Electric Code. And you'll see that there's a lot of similarities between what's in Article 504 of the NEC as well as the IEC. But you ultimately would need to follow the NEC. So let us close this and we'll continue on. And hopefully you guys can see this slide. So here's the important thing to kind of understand a little bit about intrinsic safety. It is a system concept. And when we talk about system, it's not just your associated apparatus. It's not just the end device. It's not just the control circuit. It's a combination of all of them. So we combine basically whatever our controller is, if it's a PLC or a DCS. The associated apparatus is commonly referred to as our intrinsically safe barrier. And of course, the cabling is also part of this, as well as any junction boxes or marshalling cabinets that we might have. And then finally, our field device. So, excuse me, it is a system concept, and we have to keep that in mind, especially when we start looking at our potential faults and also the selection of the devices. We need to make sure that they match and that they're safe. So there are two types of associated apparatus that you will typically find. Multiple brands, but two major types. There are what is called galvanically isolated type, or there are what are called Zener barrier type of associated apparatus. They're both known as associated apparatus. A general easy way of telling the difference between the two is that if you look at the barrier on the right, you'll see that that actually has some earth lugs, earth tabs, if you will. And generally speaking, that is a dead giveaway that that's telling you that that's most likely a Zener barrier. The one on the left-hand side is a GMI. That's a galvanically isolated barrier. And they do the same thing, but they operate in a different fashion. So there are some advantages and disadvantages of them both, which we'll talk a little bit more about. So how do they work? Let's talk about galvanic isolators first. So what makes up an associated apparatus or a barrier? If you notice on this little slide here, we actually have a current limiting resistor on the left-hand side. We have voltage limiting Zener diodes. We have a fuse that protects the transformer, and then we have a safety transformer. So what happens if we have a fault condition on intrinsic safety in a galvanic isolator type situation? We have a potential fault current that hits the transformer, if you will, and it stays within the safe area. It's not transmitted into the hazardous area. The whole concept of intrinsic safety is to limit the amount of energy that potentially could be released into that hazardous area under normal or fault conditions. That's the whole idea of having an intrinsically safe barrier or an associated apparatus in the first place. So it is meant to basically limit the amount of energy that can transmit from the safe area into the hazardous area. So this is how a galvanic isolator works. You'll typically, this is the same, no matter what brand it is, it's going to be made up of these various components. So under a fault condition, again, this is just showing you if you had a fault condition with a galvanically safe barrier, the fault remains in the non-hazardous area. And even under a fault condition, we don't have a problem in a hazardous location. So it works as if it was designed to. Now, the other type of barrier that you will find, associated apparatus, is what is called a Zener barrier. And a Zener barrier also has a current limiting resistor, we have a fuse, and we also have voltage limiting Zener diodes. But what we don't have is a safety transformer located within the barrier itself. Now, under a normal fault condition that we might have, in this particular instance, what happens is that if we have a fault and the current starts flowing, if it gets to above a threshold for the Zener diodes based upon the voltage, they will open up. So if we have a high voltage spike, what will happen is that it'll open up and it should allow all that excess voltage to go to ground. The important thing to note here is that when we use a Zener barrier, we must have a good ground connection. That is separate. That is called our clean earth, if you will. That's separate from our normal earth. So it's imperative that we do have a good clean ground to be able to allow that fault current to dissipate, if you will.
Okay.
Now, we didn't really have a question on this, but let me give you a little bit of parameters, if you will. A barrier or intrinsic safety is basically limited to about 1 watt of energy or less. So that might give you a hint on how to answer this next question. So.
Okay, let me launch the polling. We want to get feedback from our audience. Okay.
And by the way, these types of questions are the similar types of questions that you might actually find in the various competency type programs. So if you're nailing them all, that's fantastic. You're on your way. So that's a good, good. We're getting some good answers here. We'll give it another few seconds.
Yes, for a few seconds we have, let me, almost all questions, with exception of the last, has been hit. Okay, let me end the polling and let me show results, and then Bob will have some comment on that.
Yep, yep. Okay, so I kind of told you we were limited to about 1 watt of energy or less. And again, that's a generality. So in reality, what can be typically installed in conjunction with an intrinsically safe barrier? A transmitter and a simple device. And when we talk about a simple device, the standards define a simple device as a device that's a non-energy storing type device. So if we have things like capacitors or batteries, those are obviously not simple devices. But things like an RTD or potentially a thermocouple or a simple switch is considered to be a non-energy storing device, and that falls under the simple device. So we certainly can use those in conjunction with barriers. Obviously, a transmitter we certainly could use. Things like EX light fittings, we're not putting out enough energy to be able to actually drive either a ballast or the LEDs generally. So, that would not be correct, and certainly a motor would not be correct as well. So the correct answer would be B and D. All right.
Okay, so let's go to the next slide.
Okay. So protection under a fault condition under a Zener barrier application. Again, now we have a fault condition, and excuse me, here's a scenario where possibly our good ground connection of 1 ohm resistance or less is okay. But if we have that tied into our ground connection is the same as our earthing connection that we actually have in the hazardous location, we potentially could have a fault condition into the hazardous location. So we really don't want to be able to tie basically our clean earth to our what is considered to be dirty earth. We have to be very, very careful when we're using Zener barriers to make sure that we have this separation between our clean earth and our dirty earth. So as you might imagine, one of the mistakes that we do find with regards to the selection and design and installation of IS is our clean earth. That's a big issue, which we'll talk about here in just a second. So our common mistakes, as I mentioned, no dedicated intrinsically safe earth. So again, Zener barriers do, in order to work, they require that dedicated earth. And again, some of the instances when we go in and do some inspections, there's two things. We can find either that there is no earth, right? There is no earth connection off a Zener diode, or in many cases, it might be tied straight into our dirty earth. Okay, so that's kind of an all-encompassing. And again, the requirement, and this is true no matter where you look, in the NEC or in the IEC or any other international standard or national standard, basically that resistance on our clean earth needs to be no more than 1 ohm resistance. So sometimes people say, well, how big does my cable need to be? The IEC standards do tell you a minimum size, and that's 4 millimeters. But generally, it might even have to be larger based upon what type of resistance that you need to achieve based upon the length. So again, that's probably one of the most common faults that we do find when we come in and we start doing some inspections on IS systems.
Excuse me, Bob. Here we have a question, which I simplify, but how to ensure clean earth is well connected and working? That's the question.
Right, right. So, and that's a great question. So typically what we have to do in order to achieve this, it's common practice actually, and this is spelled out actually within the dash 14 standard, and I believe it's also referenced actually in dash 25 as well. We might actually have two earthing connections, and the way you would actually test it, you do a resistance test between the connection point. The reason why you might actually have two independent connections, because if you do this while it's actually in service, then we can induce a potential fault condition into it. So we'd want to disconnect one of the legs of our clean earth and make that connection, do a test, find out are we getting that 1 ohm resistance less. If we're good, then we reattach it, then we disconnect the other one, do the same type of test on that one, so it's a redundant earth. The another question that just came in, distinguish between power and signal earth. Generally, I guess what I'm considering are normal earthing requirements. That's where we have all of our potential noise. It could be the noise from our VFDs or the harmonics or just the general noise, the EMC that you would find in a normal processing facility. That's all tied into your normal earth. And that normal earth, if you will, is designed to obviously dissipate any potential fault condition. The clean earth, the problem is, the reason why we want it clean is we don't want to have induced noise, currents, all different kinds of interference that are going to be coming into that earth, because we have to keep it, if you will, we don't want to have an earth stray current come up through the earth into our intrinsically safe system. And actually, I think we show a slide about this here in just a little bit. So a lot of issues with this IS Earth, and if you see this slide here, one of the things that it's important to note, a lot of times the Zener barriers will actually use the DIN rail as a means to ground, if you will, and that is that clean earth. So the important thing to note here is that if we are using that DIN rail and we're attaching it to a metallic enclosure, then we're tying it all into the metallic enclosure. So at that point, we would want to make sure that we're using some sort of isolated, insulated standoffs between the DIN rail and a metallic enclosure to make sure that we're not tying it into the dirty earth. The slide over on the left-hand or the right-hand side actually shows, if I can see that right, I'll move these pictures of us talking here. You can see on the right-hand side, we see our intrinsically safe wiring. On the left-hand side, we see our safe wiring, and then the incoming and then outgoing, and that's typically what you would find. Notice that we have actually our intrinsically safe wiring coming out. That's our clean earth. And then down at the bottom left-hand side, that's our dirty earth that we're going to be grounding the enclosure to. So that's the normal earth that we would find within our facility.
Excuse me, Bob, but we
Right.
still have a small question about quality of earth. And the question is whether we need to carry out a resistance test
Yes.
on each and every barrier and record it.
That is correct. And actually the standards, all of them address it in a different way. I believe the Dash 14 standard says that we have to do that on a periodic basis. So we don't have to do it all the time, but we should do it during that initial installation. And then anytime that we're doing any modifications to the circuit or we're doing any work on the circuit, it's a good point to make sure that we're doing it at that point as well. So yes, correct. That's a very good point. Now, the other big mistake that we find is a lack of segregation between intrinsically safe and non-intrinsically safe circuits. So in this particular junction box that we see here, this is actually, it looks like it's probably all intrinsically safe, right? So we're finding here that we've got, this could be intrinsically safe from one side because there's no associated apparatus in there. So this just could be field wiring, bringing IS into one marshalling cabinet and then going out to the field devices. So there's all the wiring inside the enclosure is intrinsically safe. There's no exposed conductive parts of the wiring. The important thing to note is that we want to make sure that when we're making our connections into terminals that we have no more than 1 millimeter of copper exposed. Ideally, we don't want to have any copper exposed, but we don't really want to see any copper exposed on our wiring. So that's an example of a nice, clean, tidy installation. So here's another example. In this case, we have a selection of barriers mounted onto DIN rail. And then, of course, we have a nice segregation where we have the incoming power going into the barriers themselves, coming into the safe side, or I should say, actually the incoming power side onto the barriers at the top. Now, here's a scenario. This is not a good installation. So what we have obviously our power coming into the barriers and then our outgoing control circuits going to the field devices. The important issue is here with segregation between IS and non-IS. The reason why is that we do not want to induce any inductive currents that might be generated between a normal power cable into our IS system. So the minimum requirement separation between IS and non-IS circuits is 50 millimeters. So if you actually think about the design of an intrinsically safe barrier or associated apparatus, the distance between the terminals where you're actually landing and the outgoing terminals will always be a minimum of 50 millimeters. That's the actual length of the barrier, if you will. But that 50 mil separation also applies to all the cabling that's coming in and out of the barrier box. So we have to make sure that we don't bundle them all together and that we're maintaining that separation. Okay. Now here's an example of just a simple single barrier. And we look at this, and again, the power cables that are coming into the barrier at the top versus the outgoing IS. Again, it started off fine where the connections were made, but then we've run those cables right next to each other. So we have to make sure that we keep a separation of 50 mils between our IS and non-IS with all of our wiring. This is one of the things that as a designer, you can design it, but if the contractors or the field technicians aren't installing it properly, then it somewhat defeats the purpose. And this is one of the biggest issues that we also see as well besides the ground. So here's an example on the left-hand side where we have very nice segregation between IS and non-IS circuits. We're using duct and we're keeping it nice and clean. On the picture on the right-hand side, what you can actually see, there's some associated apparatus on the right-hand side, and this is inside of a flame-proof enclosure. There's actually a picture of a contactor on the left-hand side, and you'll actually see there's a partition that actually sits in between the IS and the non-IS product. So you can do physical distance of 50 mil, but you can also use things like partitions, or you can also have shielded cables, which is also an option that meets that segregation requirement. So there's different ways to do this, but be aware of that. The issue is with this installation is that we had some circuits that were exiting the intrinsically safe associated apparatus and run down right below the contactor. And what you see there is actually going into a barrier gland, into a flame-proof box, and we have no segregation between, it looks like L1 connection there and our IS. So that gives the opportunity for inductive currents to enter into our IS system, and that's a big no-no.
Excuse me, Bob. We have now a couple of questions. The first one is which barrier are having good results, Xenon or galvanic? This is quite a generic question. But...
Yeah, that's generally speaking. We're going to talk. I'll save that question a little bit later. Why don't we do that one, Mauro? Because we'll talk a little bit about Zener and galvanic.
Yes.
There's another question. There's an argument: what power cables that cause more inductive, and what's the fine line of power rating? I'm not sure what the question is there, but I'll address that one a little bit later. because
Okay.
we will talk a little bit about some of the cables. So there's, again, another picture of our segregation of IS and non-IS circuits. Again, we don't want to see this.
Yeah, here we have another question for the audience. I think you gave already the answer here, but let's see if they paid sufficient attention. And we gave you the chance to give us feedback, so you made it quite
Oh,
quite
yeah.
clear.
Yeah, you guys are paying attention. That's a good thing.
Yes, 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 yes. So give me just a few seconds again because I saw that most of you already answered. So let's close the polling and share results. Okay, I don't need to be Bob to say you are right.
No,
I was also paying attention on what you said.
there you go. And by the way, if you really want to dazzle your friends in intrinsic safety, right, there are some minimum requirements between IS and IS, and that's 6 millimeters. So for future reference, if anybody ever asks you, what is the minimum distance between each IS circuit, it's 6 millimeters. And then there is a minimum distance of IS to ground, which is 3 millimeters. So there you go. All right, so let's close this. And there is a question, what is the best recommendation when it comes to the shield to save space and cost? Metal shields have been used to avoid extra trunking. Is this a good acceptable solution as per the standard? Yeah, there's different ways of doing shielding. You could do obviously shielded cables that can save you some space on the inside of your panels. You can use partitions, as I mentioned, so that distance of 50 millimeter gets shrunk down if we go up 25 millimeter and then down 25 millimeter, so we can shrink it down that way. There's a bunch of different ways that we can address it. So there's not necessarily one perfect way of doing it, but you know, shielding and separation are both acceptable. So again, we'll skip through a little bit of this, but these are just segregation between IS and non-IS circuits. I think I've talked this one to death. So what's our third mistake? No identification on enclosures that contain IS circuits. It is a requirement that enclosures that actually contain intrinsically safe wiring or circuits must be marked. This is pretty common that we'll actually see enclosures that will be that will house intrinsically safe circuits, but they're not marked. And so it is a requirement pretty much within every standard around the world that there must be some sort of marking on the enclosure telling you that this enclosure contains intrinsically safe circuits. There's not necessarily one uniform way of how you should state it. There are recommended practices, but it's really very much left to the customer, the client themselves, but you shall designate and you shall mark that this enclosure shall contain intrinsically safe circuits. So there's, on the right-hand side, you see a phenolic tag that's actually put onto the enclosure itself. Generally speaking, we use a light blue tag. That's not a requirement, but it is, if we're going to use a color coding, we should use light blue. Intrinsically safe circuits contain. Now here's a question that we haven't really addressed yet, but I think it's this is a big question that people always ask on intrinsically safe cables. Must they be light blue?
Let's check.
And we'll see what you guys say.
Yes, this is a very, very common question. In fact, there is a debate here.
Yeah. It's always a debate.
Interesting, interesting.
We'll give it here just another few seconds for everybody. I will tell you right now, this is not uncommon. This what you guys are answering is pretty much indicative of what people.
So let's end the polling and share immediately results. was, I think you should see now results.
Yeah. So
Are you
the answer,
surprised, Bob?
no, no, not at all. Not at all. It is commonly thought that it must be light blue. However, what the standards do say, the actual answer is false. They don't necessarily have to be light blue. However, what almost all of the standards do say in some way, shape, or form. And again, what I'm telling you is somewhat generalities because every country could be slightly different on this, but generally speaking, what it does say is that if we're going to use a color coding to indicate intrinsic safety, that color coding shall be light blue. However, it does say that we can mark our cables and we don't have to use light blue cable, but we do have to indicate that cable or our wiring is actually intrinsically safe. So there is an important distinction between the two. We don't necessarily have to use light blue, but we do have to mark it. But if we are going to color code and use color as a means to indicate intrinsically safe, it shall be light blue.
Okay.
So it's a little bit of a tricky question. But the answer is false. They must not necessarily be light blue. However, that being said, some clients, some customers in the world will say, I want all my intrinsically safe circuits to be light blue. Well, guess what? The customer is always right, so it has to be light blue. But the standards do give you a little bit of leeway to be able to do some different things.
Excuse me, Bob, but before to proceed, I still have some question, both in the question and answer, but also in the chat. So I start from the chat, and the
Okay?
question is how to use a shield cable, connect to the shield, connect shield to the ground, or what?
Yeah, so what would happen, your shield, typically on your IS circuit, you would typically take that shield all the way back into the safe area. Um, Generally speaking, and this gets into the wiring regulations specifically in each country, so I don't want to get too detailed, but what I would say is that generally speaking, if we had a shield, what we would want to do is that we would typically take that shield in, say, for example, our field device. We might have our, say we have a two pair cable and then we have a shield. We would take that shield, right? And we would basically use some sort of shrink tubing or mastic or something like that. We would protect that shield, and generally we would leave that floating in the hazardous area. But however, we would take that shield all the way back and tie that in to our normal ground, if you will. The reason why we don't want to tie it in on both ends is that potentially we could create an antenna, which we don't want to do. So we want to tie it into our safe area ground um, in our control panel at that point. That's our general means of what we want to deal with the ground. There was a
Okay.
question why it's important to have an enclosure label. And the reasoning for this is basically to indicate if we're going to do any work on this circuit, we need to understand. And here's the other thing. Intrinsically safe, because it is a low energy type concept, one of the things that actually can be done on intrinsic safety is that you can actually work on these circuits live. Um, Now, I wouldn't necessarily tell you you should, and there may be many clients will say, no, you can't, you have to lock it and tag it and do all that good stuff. But actually, as the standards allow, they do allow you to work on those circuits live. So it's always good practice to understand that there is intrinsic safety in there because we want to identify those circuits as well. We want to make sure that we understand. And also when it comes to inspections, a lot of things with intrinsic safety, we can actually use products, for example, non-certified products in areas that might be hazardous location if we're using intrinsic safety. And if I'm an inspector walking into a facility and I look up and I see non-certified glands or I see non-certified pieces of equipment in a hazardous area, immediately that should be a red flag. However, if I see that, okay, it's marked intrinsic safety, okay, if it's intrinsic safety, then there's a possibility that I can use non-certified, non-EX type product. But I have to look at that very closely. That doesn't mean that I can use non-EX certified products all the time for intrinsic safety. I'm not saying that. But there is a level of flexibility when we use IS that we can do things that we couldn't normally do. So, mistake number 4, no identification used for the IS wiring. As we mentioned, you can use light blue as a cable color if we're going to use color coding. However, we can also put tags and we can put sleeving on it. We can do many different things. So, but we have to mark it. We have to say that this cabling is housing intrinsically safe circuits or conduit or however we're doing this. The cable on the right-hand side, we could use that cable, right? But we'd have to put a tag on it. We'd have to put something on there that tells us that this is intrinsically safe. So in a pinch, if you wind up and you're on a project and you find that you've got some non-light blue cable, a good solution is to get some light blue heat shrink, right? So the labeling is shall be permanent. Don't just put blue tape. That's not acceptable. We want to put something that's actually a permanent marker on that cable to identify it as intrinsically safe. Mistake number 5, incorrect gland selection or incorrect installation. Now, this applies to all different kinds of EX, not just IS, but it's also a big issue that we see with regards to installation of intrinsic safety. So this is somewhat of a generality. This goes to all the different protection concepts. So generally speaking, what we would have is on the left-hand side where we have that blue cable, we have a cable gland. In this case, we have a lock nut, IP washer going through a clearance hole. Down at the bottom, we have some barrier glands that have been incorrectly installed. We have some glands on the right-hand side where maybe the ring, the grounding is just tearing through it. So the important thing to note is that we must use the correct gland and install it in accordance to whatever the wiring regulations are in that particular country. So in general, cable glands should match the protection concept and should fit the cable appropriately. And when installed, no Teflon tape should be used. And then also look for things called traveling plugs. So down at the bottom, what you see a gland with a shroud and some Teflon tape. That's not acceptable. On the right-hand side, you'll see a transmitter. You'll see a traveling plug, if you will. That's a non-certified plug. That should be replaced with a certified plug. So those are some of the key things that we want to make sure. And then finally, what is called a missing descriptive system document, or DSD. Now, this is something that a lot of people fail to remember, that it is a requirement, no matter where you are in the world, that you need to have what is called a descriptive system document. This is spelled out very clearly in the 60079-25, as well as the other relevant standards and wiring regulations. So what is a DSD? What is in a DSD? So it gives us the information subject to the loop calculations, the components that are for use on the circuit, the wiring installation drawings, the cable lengths and or types, the identification numbers, the date and name of the signature of the designer, and any analysis of a surge protected device. And again, the installation must match the DSD. So this is an important thing that people fail to remember, is that when we're, as I think I said at the very, very beginning, remember, intrinsic safety is a system concept. So we're talking about the associated apparatus, our field device, any of the cabling, any intermediate devices, as well as the circuit. So we need to have all of that referenced within a single drawing that somebody can go and take a look at and match that up to make sure, from both a maintenance and inspection standpoint, that what's actually there matches, and that somebody took the time to make sure that they did all the calculations to make sure that all the safety parameters were met. Those are our entity parameters. So what goes on to a missing descriptive system document? And I'm just going to show you a real brief example of the type of information that you will find. So here's the information from a beacon that's considered to be an intrinsically safe. So we have our voltage input, power, ampacity. So this information is given to you by the manufacturer, right? So this is known entity parameters that are provided by the manufacturer. We then need to find, excuse me, the inductance and capacitance for a particular cable based upon a length. So we need to know that information. And there are some default parameters that are listed in the -14 standard. So we also need to find this information. And then we need to find the information on our associated apparatus, the external parameters, depending on the gas group and how it's wired up. If it's a single channel, dual channel, how it's actually done up. So taking all of this information that we just saw, what we would do is that we could put them into, and this is an example of a simple spreadsheet that can actually be the basis for your DSD. GMI actually has this, not this one right here, but actually has something similar to this online where you can actually plug this information in. So what we've done here is that we've taken the information from our manufacturer of the signaling device. We've taken the parameters from GMI, our associated apparatus. Excuse me, that we've taken the information from our cable manufacturer. And what this tells us is these numbers here. It's telling us that everything is okay from a safety standpoint, but this is the big thing right here, is the maximum length of cable is 179 meters based upon this application. So if we actually create our descriptive system document, this is what it would look like. Something like this. We have our area classification, our non-hazardous area, we have this model number, our input parameters, our output parameters, and then this information right here that's telling us that our maximum cable length can not be any longer than 179 meters. So we can use this DSD and we could have this for every circuit that has this type of device. So, and then it should be signed by a competent individual, and that should be part of the technical file that should stay with the project. So a missing descriptive system document is key and it's important. And especially if we're doing any maintenance or if we're doing any inspections on our EX system, we have to have a copy of this DSD, because if we don't know what should be there or what is actually there versus what should be there, then we don't really have any idea of whether or not it's safe or not. So it's a very, very misunderstood. It's oftentimes overlooked, but it's really important to have.
Okay.
So we have.
So we are not really closing, okay? We still have some time, but before let me say, the heart of the webinar is done, but we still have a question and answer, which we collected during the registration. But before to switch to that, there are still two questions I would like to, two or three in the meantime.
Yeah.
So I don't know whether you want to read it or shall I read it?
No, I can go, Mauro. So what is the barriers? I think the question was Zener or galvanic. These are some generalities. Zener barriers have been around much longer. These were the same devices that original IS was all Zener type products. Galvanic isolation type products have been around for the last 25 years or so now. And it used to be that galvanic isolators were significantly much more expensive than Zener barriers. But what has happened over the last couple of years, you're seeing that the cost and the demand for galvanically isolators is growing, and Zeners is not quite as much. I would always recommend personally going with galvanically isolated based upon the safety ground. So when we talk about the cost associated with with Zener versus galvanic. Zener, from a price standpoint, is typically going to be a little bit less than a galvanically isolated product. However, when you add in the cost of all the installation details with our safety ground, then all of a sudden it starts becoming a significant more expense. And quite honestly, it's, if you don't have a good safety ground, then you really have no protection. So that's usually one of the biggest faults that we see. So if you have a galvanically isolated product, then you don't have to worry about that. There was a question, the difference between a safety ground used for the motors and VFDs and signal ground, ground which is to instrument signal cable shields are connected, or ground used for Zener barrier, clean ground. Can we use the same ground for 2 and 3? So typically the signal ground and the safety ground, we would actually bond those two together. So that's the ground to instrument signal cable shields are connected in our safety ground. The ground used for Zener barriers, our clean ground, that's going to be different than the shield ground, if you will. So we would actually take our shields not to our IS clean earth, we would take that to our normal earth, okay? A question on Teflon, why it's not used. What's the consequence? And what's the minimum thread entry inside the gland has been met? So Teflon is not allowed for a couple reasons, but the main reason is, and it really has to do primarily with flame proof. If we're using Teflon, people typically would use that on a threaded entry. So if we take a threaded gland, typically a metallic gland, we're going into a metallic box, we want to use that theoretically in order to achieve good corrosion resistance or watertight protection or what have you. The issue is that especially on EXD boxes, flame-proof boxes, that thread is actually a flame path. So by putting that Teflon tape on that flame path, you've now defeated the flame path. And there is studies and there are issues with regards to putting Teflon tape onto any threads in not assuring that you're actually maintaining the explosive pressures on the inside of the enclosure, or actually you're creating what is called pressure piling. So the requirement is, almost generally speaking worldwide, is some sort of non-setting, non-hardening grease or thread lubricant on glands as opposed to Teflon tape.
Okay.
There is, please share info on the GMI template for the DSD. We'll send you, I'll get Mauro that little spreadsheet and he can send that out to you guys.
Yeah.
There was a question, different barrier parameters. Different manufacturers have different barrier parameters. If one IS calc doesn't work with one IS barrier, could one look and go with a different barrier? Mix and match a barrier would not be a good idea. No, you certainly can do that. You can find that different, I mean, the difference between one manufacturer's, on a Zener product per se, right? And I'm just going with Zener barriers right now. The safety parameters for one manufacturer's Zener product versus another manufacturer's Zener product is not going to be very different, if you will, because the components are pretty much the same. Now, galvanically isolated barriers, you could find some, I say significant, you can see some differences between one manufacturer and another. And part of that is what type of transformer that they're using, how efficient it is. So you can actually find that. And it's not uncommon to mix and match different manufacturers' products. You know, I've done a lot of installations where I've seen manufacturer A right next to manufacturer B. And so, no, that's not a problem.
Okay.
There was a question in terms of component that is it mandatory to use gold contact material when we have an EXI signal at field? I have not heard that. I'm not aware. Now, there may be something in some of the, like, for example, in the Dash 11 standard with regards to the actual design of IS, but I am not aware of anything that says it must be gold contact. So, another question, is it possible to install a barrier inside a pressurized cabinet? Yes, absolutely. one of the things that you will see on barriers themselves, barriers will be marked in two different fashions. They'll be marked, and you'll see this with maybe parentheses or brackets that is telling you that it's providing protection downstream into, say, for example, a zone 0 or a class 1 div 1 hazardous location. However, they'll have a second marking string, and in the case of GMI, they'll actually be marked EXEC, or old style would be EXNA, non-arcing, meaning that the barrier in and of itself can be installed into a zone 2 area. Now, by putting it in a pressurized cabinet, depending on the type of pressurization that we're using, PX, PY, PZ, a PX, or I should say a PYB, is taking zone 2 equipment, putting it into a zone 1 environment. So we could take barriers that are marked and suitable for zone 2, putting them in a pressurized cabinet that's rated PYB, and now you can take those barriers and put them in a zone 1 area. So yes, that can be done.
Good. Let me share. Here we have another question. It's becoming it's coming long now, but okay. Until they are here.
Yeah, until you throw us off. I'm just waking up now. So.
Well, this is a quite long question. You want me to go through?
No, I'll read it real quick. So.
Okay.
Every intrinsically safe barrier isolated has parameter tables with the CLR for every gas group, and T2C is the strictest. And actually, this is, I think, a question that we had been given ahead of time, and I meant to answer this one. So, meanwhile, all transmitters also have parameters and EX marking with group abbreviations. The question, during our IS circuit calculations, should we use parameters of the barrier according to the group of the EX area or the group specified in the transmitter characteristic? It obviously should be the group of the EX area, which in turn determines the limitations on the accumulated power in IS circuit, but I cannot find any reference to the related standards. I saw this question, and I actually did a little bit of digging, and I will answer this one offline, but it is referenced. It's not specifically referenced as the way you put it, because it is a very good question. But there is something, I believe it's in dash 14, and it's in section 16 of dash 14. So I have your contact information, and I will send you that relevant information. But basically, the answer is, it does say that we should follow the information of the EX area as well as the transmitter characteristics. So if, for example, if we're going into a 2B area, we would use the 2B output ratio or information on the barrier, and we can use the 2C information on the transmitter, but we would basically make it based upon a 2B gas group. I don't know if I'm explaining that very well, but anyway.
Okay, let me share now the question and answer presentation. I said we had, let me see. Can you confirm that you see the presentation, Bob?
I see it. Yep, I see it.
Okay, so you all should see now. Here we have some few questions, let's say, collected during the pre-registration. So the first one is how to use safety relays when it comes to IECTS 60.079.46 equipment assemblies.
Right. So the TS 46 is an assembly technical specification that the IEC has come up with. So this applies to where we have, generally speaking, a good example is that, say we have a motor and a motor starter. So the motor could be EX certified, the motor starter could be EX certified, but have we matched the motor starter to protect the motor as a system? So the technical specification dash 46 allows you to address that. Now, safety relays are part of that whole system. So when we're doing calculations and we're doing evaluation under 60079-46, safety relays are part of that. And so there's a whole bunch of information that is within the technical specification on that, which I won't go into, but if you'd like more information, we can certainly address that later on.
Good. Next question. If a component of a system is intrinsic safe, can the system be considered as well intrinsic safe? If not, how to ensure the same? And how do I calculate the intrinsic safe circuit?
Right. So, yeah, we won't go through this slide all the way through because we've kind of covered a lot of this, but uh, if a product is certified, it will be certified under what is called the entity concept, meaning that there is we have output input parameters, and then we have to match those to the various devices in the field. So just because we have a device that's certified in and of itself, we still have to look at it as part of the overall system. So I don't want to go through all the entity parameters, but basically this is what we have to do to, and this is kind of what we did in that little spreadsheet earlier, that we took all the information, and that's the slides down at the bottom. Mauro, if you go back one slide just previous on the EX verification, that's the key thing that we need to know. We need to make sure that we check all those parameters to make sure that the associated apparatus, the cable, is acceptable to the field device based upon the gas groups. And this is, yeah, oh, well, I was
Sorry,
just going to.
should I go back?
Yeah, just on that last slide there, Mauro. This is online at GMI. So this is your safety parameters verification that you can go online and you can plug in all this information and it'll generate a lot of information for you. So what I showed you was a little spreadsheet that is something that we use, that I've used, and we can share that with you as well. But this is also available online, that you can plug in all the parameters and it'll generate the information for your DSD.
Okay, here we are back again on Zener versus galvanic isolation barrier.
Yeah.
And here,
so yeah, the majority of most of your installations today are isolated barriers. Zener barriers are usually today used mostly as replacement on an installed base. Just as for your information, GMI does not manufacture any Zener barriers. That was a decision that GMI made many years ago, I understand that because the technology on Zener is older technology. Galvanic is a safer. Again, the big issue is the no dedicated earth. But again, when we talk about the cost comparison, Zener barriers typically were less expensive. However, when we start adding in the cost of all the other things, we can somehow find that Zener barriers are a lot more expensive. The other thing is that Zener barriers do have a tendency, because they are directly connected to the power source, it's not uncommon to blow the fuse on your Zener barriers during startup. This happens an awful lot. Because the galvanically isolated, they seem to be a little bit more robust, and they can handle that. So that's one benefit that you will find. It's not necessarily obvious to a lot of people. The galvanically isolated typically are going to be better during that startup process.
good. Here we have a general question about availability of intrinsically safe Ethernet.
Right. So this was actually from one of our last ones that we did, and I think Paulo had addressed this. I'm not exactly sure this was something that was being worked on. So this is actually part of a working group that's part of the IEC, the TC, SC31G. That's a technical specification that they're working on right now, but I have not seen anything on this that has actually come out. So that's where we're at on that.
Okay. Here we go for the next one. This is quite the last. We have still 3 small questions. So why IA, IB, and IC? What advantages from these protection concepts we have?
Right. So IA is suitable for all three zones. IB is suitable for 1 and 2, and IC is suitable for 2 only. So if you noticed when I showed the slide on the various barriers very early on, if you noticed that they had 3 Zener barriers operating independently, that was an example of an IA barrier. If we looked at an IB barrier, that would actually have 2 Zener barriers, or Zener diodes, excuse me. So there's actually what is called the difference between an IA and an IB and an IC is IA is considered to be double fault tolerant. IB is a single fault tolerant. IC is it's fault tolerant under normal conditions. So IC is only suitable for zone 2. IB is suitable for 1 and 2. IA is good for all 3 zones. So the concept, if you will, they all operate in the same fashion. It's more, if you will, redundancy built into the system. Um, so an IA product is going to have more redundancy built in. So hence it'll be safer, more reliable.
Good. Another question, what happens if a sensor element fails to ground when it is connected to a Zener barrier? And
Yeah,
whether Zener barrier can be used for grounded sensors in general.
yeah. So this is any fault to ground can lead to danger. So I think we've already somewhat addressed this. So I think we could probably skip on this one.
Yes, I think so. Then, can I install a ES barrier in the field, a remote area?
Yes, yes. And I think we had this question too about purging and pressurizing.
Yeah.
You could certainly take barriers and put them inside of flame-proof enclosures as well to install them into a zone 1 area. But remember, many barriers that are associated apparatus are actually already suitable for zone 2. So they can actually go into other protection concepts, enclosures for zone 2. So always look at the protection concept of the barrier itself and where it can be actually applied. But again, sometimes maybe the cable, you have to keep it very, very short. You might have to install those barriers fairly close to those field devices. So certainly purging and pressurizing or flame proof or explosion proof here in the United States is an option.
Very simple question, why a mobile phone cannot be used in zone 0?
Yeah, so so I have yet to see a cell phone be suitable for zone 0. I've seen them suitable for zone 1. They use an IB protection concept, or they can use MB, which is encapsulation. Remember, for zone 0, we have to have a double fault tolerance. And I think that's part of the design of cell phones. Nobody has been able to actually do it at this particular point in time. There are tablets and cell phones that are suitable for zone 1 and division 1, but I have yet to see anything that's actually rated IA or MA. There may be something on the market that I'm just not aware of, but so anyway, it has to be a double fault tolerant, which is going to add a lot to the cost, and certainly to make it suitable for it. I think part of it is also the fact that it's very, very difficult to achieve with things with screens and active devices like a PC or a tablet or a handheld device to make them suitable for zone 0 for that double fault tolerance requirement.
Good. I just realized it's not only 2 or 3, we have still 5 or 6 small questions, but I try to make it faster. Time's running, but we still have a lot of participants, so it looks like we are catching their interest. So let me raise the question. Potential free contact with 24 VDC relay is enough to trigger fire?
Yeah. I'm not sure where this, yeah, I think this was from a previous question, and I'm not really sure. I think Paulo had addressed this one, so I don't really remember what the answer was, but we have this slide here. So again, we'll share this information with you.
Okay, let's keep it this. I will ask Paolo, and the next time I will be able to answer. In which application can intrinsic safety be used? Okay, this is generic
Right.
questions.
Yeah, I mean, basically, a lot of our sensors, measuring temperature, pressure, all different kinds of sensor devices, intrinsic safety is commonly used. Fire and gas systems, and again, it could be oil and gas, chemical, pharmaceuticals, all different kinds of facilities. Oil and gas, it could be hazardous gas, could be used in dust atmospheres. So intrinsic safety has been around a long, long, long time. And it's been widely used. It's one of the most popular protection concepts out there. Uh, but it's only one of many different protection concepts. And again, certain things you just cannot make intrinsically safe. But for many of your sensors, your 4 to 20 milliamp type devices absolutely are perfectly right up the alley to make intrinsically safe.
Another question about the inductance and capacitance of the cable, whether they depend on isolation material of the same.
Yeah. This was something that we actually had from one of our previous ones, and we did find out that there is actually because we weren't sure about this, it was an interesting question. And we come to find out, we talked to some of the cable manufacturers, and we actually did find that depending on the cable type, even though it's the same cable construction with regards to copper, the equivalent of one jacket versus another or the construction of it can make a difference. So yes, to answer the question, the cables can make a difference. So it's important that we look at that information on the various cables. So to make sure that we select the appropriate cable, especially if we have applications where we have long runs where capacitance and inductance are critical, because again, think of the cable as energy storing. So the longer the length of cable, the more energy that is stored within that cable. If we cut that cable, we're going to induce or introduce, if you will, a fault condition into a hazardous area. So it's very, very important that we take the length of the cable into consideration for designing our IS systems.
Okay. Here we have the very last technical question, and we have a generic question, but the last technical question, what is the safety factor?
Yeah. So generally, a safety factor is 1.5. Okay. So what we're talking about here is that every one of these gas groups that we want to apply the use of intrinsic safety into, gases have what is called minimum ignition energy. That's the minimal amount of energy that it actually takes to ignite gases and vapors in a hazardous area. So if, for example, the most easily ignitable gases are gases within 2C, which are acetylene and hydrogen. They take the least amount of energy. So if what we do, we just basically say, well, what is that minimal amount of energy? And that is usually referenced in microjoules. Then we will take that and just say hypothetically it's 1,000 microjoules is the amount of energy that it takes. Then we're going to take a safety factor on that and say, well, we cannot allow anything more than 666 microjoules, or a factor of 1.5. So that's what we're talking about. That's the amount of energy that's allowed. So, and this is already built in actually to the barriers themselves, but when we have to do our calculations, sometimes we do have to, that's part of the calculation that you're actually doing.
I'm trying to, okay. Okay, here it is a very general question. It's nothing to do with intrinsic safe. It's whether we arrange webinar on functional safety and specifically on relays. I can answer to that. We still have a lot of live webinars, as I was saying in the beginning. We will run on August and September for sure. We will see whether in October we will do again. And we have also dedicated webinar to functional safety and to selection of relays. So have a look to our website. You will see the upcoming one, and you can select the one which is of interest for you. And before to the last question to the people, we still have some question,
Yeah,
live question. It is
yeah,
quite
Mauro,
long, so I would
yeah,
give you.
let me just, I'll answer these two real quick. Um,
Okay.
There's one question, can we mix IS and explosion-proof concept in the same hazardous area, e.g. motors, explosion-proof, and two transmitters IS in the same area? Yes, absolutely. There's nothing that states that, I mean, from an EX perspective, it's very common to use different protection concepts in the same installation. So yes, you certainly can. And then the other question was, while using testing calibration of IS equipment, different apparatus have been used and hooked up and somehow has become part of, oh, I'm not sure where that went to. But I think there was a question as to if you find that there's additional items that have been hooked up to that loop, if you will, how do you address it? Well, you would have to basically at that point revise your DSD, right? You just have to go back and then you have to find out, okay, by introducing additional items into my loop, has that affected my safety? And if it has, then we're going to have to go back to square one and restart over. But if not, and it's still safe, then we just revise our DSD to reflect actually what's been put in.
Okay. Here we are. We have a very last question to the audience.
Yay!
I will launch the last poll. Just I want to say, keep in mind that somebody is waking up at 3:30 to run this webinar. And so, but I think,
Thank you,
good.
Mauro.
No, we are, you are getting anyway, very good result. So, um, just few seconds again, even you are really answering so fast, and most of you answered. So I can only say thank you very much. I end the polling now and share proudly the result. Thanks, Bob. Really, very good result from you.
Yeah, and Mauro,
Very well deserved.
well, thank you, Mauro, and thank you everybody for paying attention. I enjoy doing this, and it's fun. It's great. Please feel free to reach out and contact me if you have any questions. Like I said, I actually have my own company in Houston. I have a GMI email, although I don't seem to get any GMI emails, but I do have another email address. It's bob.johnson@sourceiex.com. And you can get a hold of me anytime, and I'll try to answer your questions offline. But
Yeah.
thank you so much, Mauro.
Oh,
Eat
yes,
safe, everybody.
just few words, just to remind what I said already. Uh, you will receive all PDF presentation of the two presentation, including question and answer. You will have the chance to re-watch the presentation on our YouTube website, and you can go on our website and you can register for any further training webinar on intrinsic safety issues, on functional safety issue, and other practical arguments that we will go through. So thank you very much again, and all the best to all of you, and thank you again for being with us.